Let's talk about systematic reviews. Systematic reviews and meta-analyses are studies of studies, and they sit atop the evidence hierarchy. They enjoy this status because they synthesize the best available evidence. The goal of any literature review is to summarize what is known about a topic. A systematic review is a special type of literature review that is used to answer a specific research question through a systematic search of the literature and critical appraisal of study designs, methods, and results. Some systematic reviews also involve meta-analysis, which is a quantitative approach that combines the results of multiple studies to estimate an overall effect size. Three excellent sources for finding systematic reviews in global health are the Cochrane Library, the Campbell Collaboration, and 3IE. For health-related reviews, you can also search PubMed using the Clinical Queries feature. Systematic reviews are typically big projects that involve a team of several people working over several months or more to complete the work. This work always starts with a clear research question and a strategy for finding every piece of high-quality evidence that answers the question. We'll hit some of the highlights in this process. Along the way, we'll use a systematic review of the effects of chemoprevention on malaria by Radeva Petrova and colleagues as our example. Take a moment to download the article. PICO is a helpful mnemonic for developing research questions, particularly when you're interested in the impact of some program, policy, or exposure on a clinical outcome. P stands for patient, problem, or population and specifies your target group. In this example, we're interested in pregnant women living in malaria endemic areas. I is the intervention or exposure, and here we're interested in any form of malaria prophylactics. C is the comparison group. Prophylactics versus what? We'll say versus nothing, a true control, or a placebo. O is the outcome. Systematic reviews will often report on more than one outcome. Here we'll just say parasitemia, the presence of malaria parasites in the blood. Putting it all together, we get, among pregnant women living in malaria endemic areas, does chemoprevention reduce the risk of parasitemia compared to no treatment or placebo treatment? The methods section of a systematic review should tell you everything you need to know to reproduce the literature search, including details about the databases searched, start and end dates, and supplemental strategies such as checking reference lists and asking subject matter experts for unpublished data and reports. Often you'll find a table like this one in the appendix that gives you precise instructions for replicating the search in different research databases. It's customary to prospectively register study protocols for systematic reviews. This lets researchers avoid duplicating work and helps to make transparent any changes between the planned strategy and the actual strategy in the published paper. Prospero is a commonly used registry for systematic reviews. Search syntax varies a bit across databases, so check with a research librarian for tips. This graphics shows you how you might implement the search strategy from our example in PubMed. This flow diagram is typical of what you'll find in any good systematic review. The authors screened a total of 179 unique records against pre-established inclusion and exclusion criteria. First, they screened each title and abstract and excluded 126 records, leaving them with 53 articles to examine more closely. After a full-text review of the subset, they excluded an additional 31 records, leaving them with 22 articles describing 17 different studies. Once you have a set of included studies, the next step in a review is to extract key data points from every study. This often includes details like the study design, sample size, and effect size estimates. Many teams will collect this information in a simple spreadsheet, but there are also specialized software programs to help you manage the work. Critical appraisal follows data extraction. The goal here is to consider how the results of each study could be biased away from the true estimates. Now, we never know the capital T truth, so we talk about the potential for bias. In the case of our example review, two of the authors worked independently to extract key pieces of data from each study and assess the risk of bias using something called the Cochrane Risk of Bias tool. This tool covers 7 domains of risk and asks review authors to provide a rating for each study on each domain: high risk, low risk, or unclear risk. The graphic you see here is typical of what's reported in Cochrane reviews. If a systematic review includes a meta-analysis, the next step is to pool the results across studies and estimate a pooled or a meta effect. More on this in a moment. The final step in the process is to draw conclusions based on your assessment of potential bias, the strength of the evidence, and potentially the results of a meta-analysis. The example authors concluded that chemoprevention during pregnancy prevents moderate to severe anemia, and the evidence that is high quality. Now let's talk about meta-analysis. This is a forest plot, a very common way of summarizing the details of every study included in a meta-analysis, along with the pooled effect size. Take a moment to examine this annotated example. Each row describes a single study. It's customary to show the sample size in each study arm, the estimated effect size, and the weight given to each study. Effect sizes represent the strength of the relationship between group assignment and the outcome. Relative risk is one type of effect size where a value of 1 indicates no effect. When the outcome is something bad like malaria, a value less than 1 means a reduction in risk for the intervention group. The size of the symbol corresponds to the weight of the study, and the width of the horizontal lines represent the confidence intervals around each estimate. The final column is a numerical summary of that graphical display. Here's one of the forest plots from our example study, summarizing the effect of chemoprevention on parasitemia. Let's focus on the second study in the list by Greenwood, 1989. The denominators of the intervention and control column, shown as capital N, show that 21 people were assigned to malaria prophylaxis. That's the intervention, and 13 were assigned to the control arm. The numerators, here lowercase n, show that 4 people in the intervention arm experienced the outcome, parasitemia, compared to 5 in the control arm. The final column shows the estimated effect size as a risk ratio. This is simply the ratio of people with parasitemia in the intervention group divided by the same ratio in the control group. The point estimate here is 0.50. That means that malaria prophylaxis reduced the risk of malaria by 50%. The shapes and lines show that this point estimate and confidence interval graphically. The size of the square is proportional to the weight of the study, and larger studies are generally given more weight. At the bottom of the forest plot, you'll find the weighted meta or pooled effect size that combines the results of all studies included in the review. In this case, the pooled effect size is even bigger than what Greenwood found. Our risk ratio of 0.39 means that malaria prophylaxis reduced the risk of malaria by 61%. One question we always ask with a meta-analysis is whether the set of studies should be compared as a group or separated into smaller groups that are more alike. This gets at the idea of heterogeneity. If the individual studies vary a lot in their conclusions, we'd say that there's a lot of heterogeneity. For instance, it could be the case that the review is trying to find the pooled effect size from studies that look at very different populations. In this case, it might make more sense to pool the results within each subset rather than overall. Or maybe the studies use different methods or differed in their approach to the analysis, and these differences account for the variation in outcomes reported. Here too, it could make more sense to look at the pooled effect among subsets or just take a different approach to the meta-analysis. Here's the forest plot again from our example. Look to the bottom for details about heterogeneity. A good recommendation is to look at the I-squared value as a measure of inconsistency. There's no hard cutoff, but studies with an I-squared value greater than 75% should probably address heterogeneity in the analysis. In this example, the authors concluded that the observed heterogeneity is expected given the real-world variation in malaria severity and treatment protocols. Finally, summary of findings tables like the one shown here are a common way to distill the main lessons of the review. The first column shows the typical burden of the outcome as an illustrative risk, basically what you'd expect in the absence of the intervention. The second column shows the absolute risk with the intervention. This is followed by the relative effect that we found on the forest plot in the previous slides. The table concludes with the number of studies and participants behind these estimates, as well as a grade of overall quality of the evidence. A grade of high means that further research is unlikely to change our confidence in this estimate of the effect size. It's based on the size of the effect, the number of studies, and overall sample, and the quality of these underlying studies.